Okay, hello folks, and welcome to my usual Wednesdays hacking podcast, or actually a live stream with whatever is the difference. Anyway, I'm just checking if my microphone actually works, and it does. I can hear myself perfect. There's about a 10-second lag between me casting and actually missing myself on YouTube, so that should be fine. So, as always, welcome and good evening. Today's topic will be race conditions. Actually, the basics of race conditions. It's well, two last topics were things I was not super familiar with. It was WinDBG, which I rarely use, especially for user mode debugging, and then it was heap-based exploitation. Or actually, it was like the basics of heap, trying to get a feel of how the allocator actually works by doing some experiments. Today's topic is a little different, since I felt like the need to actually get back to something I am quite comfortable with, and race conditions is something like that. So yeah, so it turned out that today we'll be doing race conditions, and actually somebody also proposed this topic, so I just jumped on it. One important announcement: the next live stream will be about Binary Ninja plugins, writing Binary Ninja plugins, and my guest host will be Karstein, or Michał Malewski, who will be showing how to write such a plugin. He has I'll introduce him, I guess, next time, but he has a blog, which, like, some of the recent posts are basically on that, about Binary Ninja. So if you're wondering, like, how the API differs from IDA, and is the API good in Binary Ninja, and I believe, like, the scene is gone, thanks, it is good. So, yep, join us next Wednesday, and we'll be talking about that. Then the stream after that will be on format string exploitation. That's another topic I'm quite fond of, and I actually like that back class a lot, even though you don't see it that often nowadays. So yeah, that's the plan. Apart from that, let's see what do I have here? Oh, I actually have some change in the graphics of, like, the art, but you cannot see it on this scene, but you can see it on this scene. So I didn't yet configure everything properly, but this is basically how everything will look like when I'm finished with it, including all the other scenes. So I hope you like it. I actually really like it. So and yeah, obviously it wasn't done by me. It was made by a graphical artist, which I hired. And the person is really good. So, first of all, or actually, I don't know, third of all, fifth of all, whatever, KrzaQ is today's moderator. Thank you for being here. If you have any questions at any point in time, then ping this guy on IRC, or ping him on YouTube chat, and he will let me know that there is a question. I think he's still configuring our voice chat, so if you have any questions right now, he'll probably not get it, but once we get going, then yeah. Apart from that, this is his blog. Like, oops, I did click something I was not supposed to click. Yeah. devkrzaku.cc. KrzaQ is how you pronounce it, actually. It's a Polish pronunciation, so there you have it. Apart from that, Live Overflow, which I'm always basically advertising his channel every single time on my live stream, since I really like his channel. It's like Live Overflow on YouTube, or just youtube.com/liveoverflowctf. He has a couple of new videos, and that's like on really hot stuff, like Nintendo Switch. I believe there are some, like, WebKit bugs there. On SH1 collision, I did mention it on my previous episode, and he actually did a podcast on it, which is really cool, a 6-minute intro. And apart from that, there is some other stuff, so yeah, totally check out his YouTube channel. And the last thing is, if you have Windows, update now. And by now, I mean probably in the next few days. Yesterday it was Patch Tuesday, and there is, let's see how many CVEs. It's not 135, because there were 6 or 7 CVEs in January, and then there was nothing in February, and the rest is like over 100 is just yesterday. That's how many bugs were fixed yesterday, and that's and you know, CVE numbers are assigned actually to usually, like, moderately to critical bugs, so that's a lot of fun here. Now, quite a lot of this is basically because of Mateusz Jurczyk, or Euro. I'm sorry, that's not what I meant to press. And as you can see, like, it's just a steady stream of Uniscribe remote code executions and Uniscribe information disclosures. Like, I don't know, quite a lot of them. I think around 30 or 35. So, yeah, update Windows if you're a user. Now, let's chat about race conditions. Race conditions are actually a fun bug. And let's see, KrzaQ is still not here. So let's start with the basics, and then we get into. I maybe write some. I'll probably write some program to show it, and how I'll also show how to increase the size of a time window in certain conditions, but we'll get to that. If you go to vexillium.org/pub, it's actually, this is how you spell it. It's double L and then like I's from like on both sides. It's like a place we keep with our published papers, and there's this one, identifying and exploiting Windows kernel race conditions via memory access patterns. That's something I'm going to talk about today as well. And another one, which is kinda a race condition, is this one, or actually the work that was later done on it is PHP LFI to arbitrary code execution via blah blah blah. This isn't a bug. This is an exploitation method of LFI, so that's an important distinction. It's like a technique, it's not a vulnerability by itself. Can I still update to Windows 10 for free? I don't know. I think it was like doable up until sometime last year, and then they said like you cannot update anymore, and then they changed their mind and said you can still update, but I have absolutely no idea what's the current state. I need to create a directory for race conditions. Here we go. Okay, and I'm probably going to need... I'm going to do some drawings today. Using my mouse. I need to connect my tablet still. I have no idea why I haven't done it yet. Okay, so what's a race condition? Basically, a race condition is a situation where you have basically two events in time, and and these are like trusted events, or events created by a trusted party. And then there's an untrusted party who tries to have an event influencing these events, somewhere in the middle. Basically, yeah, if you have a timeline, right? This is the timeline. Then you have some event, usually it's a check. Yeah, I'm going to just write CH, I'm not going to write the whole word. And then you have another event, which is use. Therefore, it's not the only class of race conditions, but this is one of the popular subclasses of race conditions, which is called talk-to. Talk-to, and by talk-to is an acronym, means time of check to time of use. It's talk-to. That's how you write it, how you pronounce it. Time of check to time of use. Yeah. I'm going to just say talk-to today, so yeah. So that you know. Okay, and basically you can assume that both of these events are done in one thread or in one process running. Let's talk about local race conditions first, since that's most interesting. Let's assume we have one trusted process running en route, and you create it. For example, checks if a file exists, for example, and this is the check. It checks if the file exists. And then, well, let's say the file doesn't exist, and this is what it actually is looking for. And if the file doesn't exist, then it opens it, giving it a flag that, hey, if it doesn't exist, then actually create it. And then it does some operations, some writing to the file. Now, this is quite important, because if the file would exist, it would actually, for example, select a different name. Think about temporary files. And this is done, the file is actually written into some public directory, into a space where the attacker can actually influence it. For example, /tmp is a good example of that. And that's usually also the case. Now comes the attacker, and the attacker tries to race it, as in to create another event in time, let's say here, somewhere in this window. This is called a window of opportunity or a time window. And the attacker creates a file, and the file of that exact name. So the trusted thread checked that the file doesn't exist and proceeded to open the file with giving it a flag that, hey, if it doesn't exist, then just create it. But at this point, the file already exists because the attacker just created it. Therefore, all the data which is written into the attacker-controlled file, and by that I mean that the attacker is able to read from the file, for example, because, for example, the attacker has the file already opened, and also the trusted process which would normally set some restrictive set of rights so that the attacker couldn't open the file. But since the attacker actually was the one creating the file, now the attacker can open it. And it's called racing or race condition because, well, you do have to hit, as an attacker, you do have to hit your event somewhere in this time frame, somewhere in this window of opportunity. If you, I don't know, like create the file too fast, right, then, well, it checks and the file is there, so it chooses a different name. And if you create it too late, then it already opened the file and already created it, so you as an attacker will not be able to create the file of the same name. And I'm only talking about files this time, but it's actually not restricted to files only, since, well, it can be anything, and I'll actually show you some other examples soon. But yeah, this is basically the basics of race condition. Now, this window of opportunity, which is a quite interesting concept, can be large. It can be, for example, I don't know, 5 seconds. 5 seconds, it's a lot of time in computing. That's like ages. Even if it's like a remote race condition, as in you have one server and then you have your computer and you try to inject an event like in a kind of controlled way, then 5 seconds is a lot of time and you can do it remotely. But this window of opportunity could be like, I don't know, 5 cycles, right? 5 C with as CPU cycles. And that's not a lot, that's like nanoseconds. And this is rather heavy to actually do it. So what you end up doing is you end up usually writing a loop, and in the loop you try to trigger this set of events, like trigger the trusted process to do this talk to, right? And then you actually do, and then you try to race it, as in you're just basically spamming with these events and in hope that you at some point you hit this time window. Yeah, so that's how it works. Now let's go to some more fun examples. I'm actually going to talk mostly about today another case, and let me maybe discuss it. So I'm going to move this. Yeah. And another case is, so now I discussed 2 processes running under 2 different users, or for example 2 servers, right? Or like a server and a computer. But you also talk about race conditions in another case where you have the kernel and some code running in the kernel, and you have the user mode process, right? So the user mode process has, for example, 2 threads. And this is the kernel code, it's trusted. This is like ring 0, right? So 1 ring to rule them all. And then as a user, you have 2 threads. And you have thread 1, and then you have thread 2. Now, in thread 1, you do a syscall. Yeah, let's maybe change the color. Yeah, you do a syscall. Whatever syscall, but the syscall has to be vulnerable to this specific type of bug. And you tell kernel that, hey, listen, in the syscall, one of the parameters is a pointer, and it points to some area of user memory, which obviously is again in user land, in user memory. So the kernel has to access this memory in order to get the data from it, right? So it accesses it and gets the data, and then uses the data. Now the problem is if you actually are able to, if the kernel has a bug in the given syscall or a given driver, that it first accesses the memory which it pointed to, and it does checks. For example, there is some field here, right? And the kernel checks, hey, is this field, I don't know, larger than 12? if it's, or actually like the other way around, if it's smaller than 12, and let's say 12 is the size, for example, then everything is okay. Otherwise, exit, because this is an invalid call. It's because we expect the structure to be 12. So this is the first part of talk2, right? It's time of check. This is the check time. And then the kernel does it again. Like, it already checked that the size is valid, and then it accesses it again and takes the 12 and uses it. Now, in the meantime, what the attacker could do is, having the second thread, it can override this value with a different value, like, I don't know, 60. And if it was the size indeed, and there is some copying going on, there is some possibility that actually the syscall, there will be a buffer overflow in the syscall because the size mismatch, right? So isn't everything vulnerable to race condition? No, and I'll explain you how you can actually fix this situation in a second. But yeah, basically it boils down to a second thread changing this value really quick and alternating between 12 or whatever, like, I don't know, 8 for example, whatever meets the check and whatever doesn't meet the check. And the thread number 1 is actually spamming with the syscall, like calling the syscall after syscall after syscall after syscall in an infinite loop. And yeah, basically what the attacker tries to do is the attacker tries to again hit the window of opportunity where the check happens where this value is present, but the use happens where another buffer size is present, and the kernel can then, for example, overflow. And yeah, and what this gives you is a local privilege escalation, which means you suddenly get, for example, in the end, right, if you are able to exploit the buffer overflow, you get, well, code execution with ring 0, and having code execution with ring 0 basically gives you root access to the machine, or even greater access than root, actually. Yeah, so how do you fix this situation? The fix is actually trivial, and what you do is, let me maybe move here. So what you do, again, if you have the user, right, and the kernel, and the user does a syscall and again points to a fragment of memory, right, and does a syscall, the kernel is supposed to take this memory, the whole piece, everything it needs, and copy it into kernel space. And it does a copy here, right? The memory is copied, the field is copied, and from this point on, the kernel is going to use only this copy. And because this copy is in kernel space, in kernel memory, user doesn't have access to it. And user cannot have another thread racing it, because, well, it can access its local copy, but it cannot access the copy which the kernel made in the syscall handler. So this is the proper way to do it in this case. And if we go back actually to my explanation of race condition here with the window of opportunity and creating, first checking if a file exists and then creating if a file doesn't exist, then, sorry, I spilled some tea on my desk. Yeah. So what you do here is you do it in a different way. You create a file, and while creating the file, you specify that you only want to create it if it doesn't exist, so a different flag than I mentioned. I previously mentioned the flag. Create the file, open the file, and if it doesn't exist, then create it. You want to do it a different way. You specify the flag, then create the file, but if it exists, then fail. That's one thing, and the other thing, on creation, you have to specify the security descriptor of the file. You have to tell the system that actually, like, only I want to access it and nobody else should be able to access it. That actually gets quite funny. Let me launch a Linux console and I'll show you why. And for example, let's do fopen. Fopen is a standard way to both open and create a file, right? Now this mode here, tells how to open the file. Should the file be opened in read mode or write mode or append mode or binary mode or text mode on a different axis, but you cannot specify in fopen really like what privileges would you like the created file to have. For example, you know, like 0, 6, 0, 0, my handwriting is terrible, which is like only I as a creator can access it, but nobody else can. V0 say nobody else has access. So you cannot specify it, but if you go into low-level APIs like Open, for example, this is totally not the API I was looking for. I guess it's in the second section. Then you actually have a way to specify the mode, and this is exactly the way you should do it. As in, create a file and specify 066 and then adjust the rights accordingly. For example, if you want to add some users to be able to access it using ACLs and so on. Okay, I see there are some questions, and I'll get quickly through them, and then we'll go into actually playing with this scenario, since I find this scenario a little more fun than the other one, since the time window here is really short. And it's really short because, well, you have, check the value, and that's one assembly instruction, actually 2 assembly instructions, right? And then you have, like maybe a jump, and then you have another, then you have use instruction. And it's like 3 assembly instructions. How can you raise it? It's like 2 cycles or 5 cycles. You can. And I'm going to show you some tricks on how to do it, and that's basically mostly based on the research we did with Juru, with Mateusz Jurczyk, and also based on common knowledge which has been on the security scene for a while. Okay, so questions. Not related to today's topic. What is the best book for learning internals of operating systems in general? No idea, but if you're so in general, it's a hard thing, but for Windows internals, like Microsoft Windows internals, that's basically the most important book for anyone who is doing research on Windows. So let me find it. Internals. It's basically they issue a new copy every a new edition every year, maybe every 2 years. It's great. It's quite thick. Actually, now they have two volumes of it. So, but yeah, you have to read it. I have absolutely no idea for Linux. I know there were some older books about Linux kernel and internals. I have no idea now. There are some books for about operating system algorithms, which are used, for example, when doing swap memory or virtual memory, or when doing disk access. But that's not really when it comes to security. That's not super important. I know there is a book on FreeBSD kernel. I have it lying around somewhere here, but I didn't get to it yet. I don't remember the title, sorry. So yeah, if you're into Windows, and if you're into OS X, there's OS X kernel hacking. I don't remember it. I don't remember the name. I do remember the cover though. Maybe there. No, I didn't see it. I need to look up the title. It was a rather thick book, again, with quite a lot of details, quite a lot of fun stuff. So I need to look it up. Okay, how can we write secure code? Do you know some resources, books, sites? Yes, what was the site name? I'm going to add some links into the description to the comments under this video, since I actually knew of the site. But so it's basically go to OWASP if you're into web security, right? OWASP.org. OWASP.org is like Open Web Application Security something project. They have quite a lot of stuff here, and then there is another one. Sans Secure Guidelines. Yeah, I think this is around it. Yeah, I think this is it. Yeah, this is it. It's like securecoding.cert.org. They have basically per language, they describe common vulnerabilities in each language and go through how they look like, how you should be able to avoid them, and so on. So I'm going to, I guess, copy this link here and here. And well, OWASP is pretty easy to remember, but I'm still going to put it here and here. Okay. Isn't everything vulnerable to race condition if you spam quickly enough? This is something I already addressed. Basically, no. You can do it in a secure way. For example, it's in the way I showed just like a few minutes ago. Cannot thread to change the size of a whole object before it's copied into kernel space. Yes, it can, but if it changes, then the kernel does the check after it copies the object already, when the object is already in kernel memory. And therefore, well, you change it, but it will just fail, because it does the check and it sees that the size is incorrect, so it just fails and says, no, like exit syscall, we are not doing it. So both the check and the use in that case are done on a local copy in the kernel, and therefore the second thread is not able to change it, because the second thread doesn't have access to it. And the important thing here is the change, right? You need to actually be able to modify this value. If you don't modify this value, then yeah, that's the beauty of race conditions, right? That you have 3 events, one of them being being the switch. It's a bait and switch, basically. So now let's create an application which has 2 threads, and I'm just going to show you just with one application and 2 threads how to, or maybe 3. Yeah, let's do 2 threads. How can you, or maybe even 1 thread, whatever. How can you make sure that you have more than 5 CPU cycles to actually exploit a local race condition? Since that's the fun part here. I'm going to do it under Windows just because my Linux is on a VM. I could run on some shell, but yeah, let's do it on Windows. So I'm going to what do I have? GCC 64 bits, perfect. Test.cpp, I don't know if I will be using C++ or just C with classes, but we'll see. That's one thing, and the other thing is I never remember. So there's this create thread API, but it has like 75 parameters. And by 75 I mean 6, and I never remember the order, nor is it important enough. Yeah, and now we just create a thread, and we could actually create a thread in C++ as well using std thread, but whatever. Okay, no security attributes, size can be 0, that's the stack size. If I put 0, it's just the default stack size, which is okay. Start address, I'm going to need to create this kind of a routine somewhere here, so I'll do it in a sec. I'm going to call it my proc, for example. My proc, and then parameter, I will have no parameter. I'm probably going to just use a global variable. Yeah. The creation flags, I don't think there are any important creation flags. Create suspend is sometimes useful, not this case though. So 0, and there's some thread ID. We need to probably save the thread ID somewhere. I don't think this can be null. So did equals 0, let's just initialize it and put it here. Okay, so this should create a thread, and in the end we need to close the handle, close handle hth. I need to include some API. No, I don't remember, well I kinda don't remember, I do remember how this should go. It should be like dword, when API, my proc, and it takes I think like a LP void, which is actually a void pointer for a parameter. I'm not going to give it a name though. This was my proc something, but let me make sure. Yeah, it's like this. It's exactly like this. So perfect. No, it's like, yeah. LP void. This is already a pointer, but the P here stands for pointer. So now I'm going to assume that there is. Yeah, let's do it like this. I'm going to create a global variable, and the global variable will be volatile. So volatile, what it tells the compiler that the object or a variable, well, variable is also an object, but never mind. An object which is specified after it can change in a way that the compiler is not able to predict. So the compiler needs to read from this object each time it actually references the object, because otherwise the compiler would just like fetch it once from memory, put it in a register, and don't care about the memory at all. It would just use the register value, and we want to prevent that, and volatile is a keyword we need to use. And there's going to be a D word. Is it going to be a D word, or is it going to be... I think I'm going to make it a little more complicated. Yeah, I don't know how many volatiles I have to put here. Let's try maybe this one. This should be enough. And this will be a pointer to some D word, right? Now, in here, I'm going to do an infinite loop, which will call a function, and this will actually emulate the function will emulate a syscall, but we're doing it in the same user mode process, but it doesn't change anything. I mean, you exploit kernel mode the same way. Okay, and what do you do here? I don't know, like fake syscall, let's just call it like this. And the fake syscall will use this global variable. I am not going to pass it here in any way. So void fake syscall, and what the fake syscall is going to do is going to check if ptr is equal. No, I'm going to actually change it. It's going to be a bool, and I'm going to check how long does it take before raising it. So yeah, if it equals 10, then 10 is just a like random magical value. Then if it equals the same thing, if the same thing equals 5, return true. Otherwise, return false. So as you can see, the window of opportunity here is like between these two lines. That's not a lot, but it should be enough, especially when we start doing fun stuff with it. And so this is our... what I'm going to add here, I'm going to add some time measurement here to see just how long will it take us to do the race condition, right? Now, how do you measure time in such case? Because the time might be either large or small. If you actually go to my blog, but /n for nodes, there is something called resolution and update intervals of different time fetching functions. Because, you know, when you have a time fetching function, for example, I don't know, time, right? It has two properties which are important. First is the resolution. What unit does the function return? For example, does it return in milliseconds, or does it return in seconds, or does it return in nanoseconds or days, right? So that's the unit. But the second factor is actually the update interval, meaning even if you have something, a function which does return in milliseconds, it doesn't mean at all that that the values there that you will see will change like by 1 millisecond. The values might actually be updated, the values of the timer might be updated every 100 milliseconds, so your resolution is actually rather bad there. And yeah, and for example, let's say, I don't know, we have this clock function on Linux that is not really specific to Debian. And even though it returns, I don't know what it returns. I think it returns like nanoseconds or yeah, I think it returns nanoseconds. Then it's still updated every 10 milliseconds, which means that, yeah, that resolution is not really great. Therefore, I can, I guess, use clock from Windows. It updates every 1 millisecond. Millisecond isn't that great, but we might, what's better? Clock get time is better, but query performance counter. I'm going to use query performance counter probably. Yeah, let's just use this API to get the time. Because I want to measure how long will the race condition take, right? So I'm going to create two large integers. Large integers, if I remember correctly, just a structure. And then I'm going to query the performance counter twice. It returns like the same thing, I think, as no, what does it return? because it uses the cycle counter on the CPU. I don't remember if it translated to like nanoseconds or something. Yeah, well, it doesn't matter. As long as the value changes, it's good for us. Now, I would actually... This is a union, I think, of 64-bit integer and two 32-bit integers. Yeah, and quad part is what I'm interested in. So, I'm going to print... I'm going to first do longs, fine. Deltas in a difference of stop.quadPart, and we subtract from it the start quad part, and this is the delta, obviously. And now I can print f LLU of this, which is the time it took, right? Okay, cool. So if we never win the race, it will just keep going and never print anything. And when it wins the race, it will tell us how fast did it win the race. And now the racing itself. So the racing will be rather easy. It's also another infinite loop for like forever, because why not? This will if this will kill my CPU, then my stream will start lagging a lot. But so yeah, I hope it won't affect. I have quite a lot of cores, it shouldn't affect too much the stream. So pointer equals 5 and pointer equals 10, and I'm going to compile it. Yeah, just swapping the values, right? This is all I'm going to do, just swap between the two values, and then this is going to test the two values. Cool, now we can compile it, I guess. What is the name of it again? Test CPP. Let's see if it compiles at all. Let's C++. Okay, let's do this. What Linux distro has the best name? That's actually an interesting question. I never thought about this problem. I don't know. Okay, what does it... I'm pretty sure it supports this, but... whatever. It's the old problem of Windows actually having different naming conventions for the formats of 60-bit integers than Linux. I think that proper Windows one was like i64u or something. Yeah, maybe just i64u. Yeah, okay, now it's fine. But it would work too. They fixed it in the newest CRT versions. Yeah, so I'm going to launch it and see if it... it actually crashed, that's funny. Why did it crash? Oh, because I didn't actually put this... Yeah, let's create first a variable on the stack. P equals 0, and ptr is going to be pointing to this. This should be fine. Yeah, and it took 2 or 0 cycles now to actually raise it. That's quite fast. Which is unfortunate because it won't... I won't be able to show you how... or will I? Okay, yeah, still I can show you the tricks, because why not? So, how to make it more difficult? You know, first I'm going to do something else. First I'm going to do this mass intel and see what kind of what kind of assembler it actually generates, just out of pure curiosity. And it, let's maybe do it like this. It generated this file. And this file, this is actually the fake syscall function, right? And this is the time window. As you can see, it actually... is this the time window? Why is it relative addressing? Not that I care by why is it? Well, okay, it's relative addressing. At first... No, seriously, why is it relative addressing? No, okay. I don't know. Whatever. That doesn't matter at all. So this is the time window actually between first fetch of this value and then the second fetch of this value. That's quite a lot of time. We could decrease probably this by, I don't know, fetching it twice to the register and something, and then doing it. But so I'm going to actually change the game because it happens so fast. I'm going to change the game and ask how many times per second can we raise it. Another thing is that I actually might have screwed up something here. Compiled with dash. Okay, let's see if this actually. Yeah, let's see if this changes anything. Let's see what kind of code was generated. The code that was generated was this. Yeah. It does increase the complexity of the problem, so I'm going to actually use this method. But it still is super fast. Why is it so fast? Usually it takes longer. Okay. So one of the reasons it usually takes longer is because the fake syscall has, you know, some overhead on when you call it and overhead when the other way around. So I'm going to add some overhead in the means of this. Sleep 0, it basically just tells that, yeah, this process basically wants to yield the CPU to some other process. This thread, obviously. Yeah. Now it takes a little longer, sometimes it still takes not a lot of time. But yeah, I guess we can, I still will not be able to showcast it to you, unless I do also another sleep here. I'm trying to emulate a syscall, which, as you can see, doesn't work too well since various condition is one really fast. Still, I'm going to talk how to make it even better, how to win even more per second, because this is what it boils down to. How many times per second can you win? So you know what I'm going to do? I'm going to actually remove these, and I'm going to change the game into how many times per second can we win. So, or actually no, even better, I'm going to still have this, but I'm going to introduce a counter here. Yeah. Blah, 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 and I equals 0. Yeah, probably this is the best method. So if this is actually 1, then I++, yeah, and let's see how it goes. Okay, then even more. I absolutely don't trust this measurement, but let's assume this works. Okay, so now to win 10,000 times the raise, you have to. There are some questions, I'll get to them in a sec. Yeah, to win this amount of races, it still takes this amount of units. Now, I'm going to show you some ways to optimize it. Even though it's actually really fast, you know, when it comes to real exploitations, you do want to optimize it. So first of all, let me show you what's happening right now. Currently, we have a variable on the stack, right? So we have a, let me move it. So we have the memory, right? And there's somewhere the stack region, and we have a variable there, and ptr actually points to this area. Now this is a dword type, which means the address here, it's actually going to be a multiply of 4. It's going to be evenly divided by 4. So it's going, you know, in hexadecimal address is going to end either by 0, 4, 8, or C. The end of the address of this variable, and we can actually like check it really easily, but yeah, just trust me on this one. Now, access on x86 to this kind of variables is actually really fast. Now, it's fast because, well, because of a couple of reasons. First reason is that, let's chat about cache, for example. We have, you know, the CPU, right, has different layers of cache. So there's like the bottom layer, the so-called level 1 cache, there's actually one for code and one for data. And then there you have L2 cache, and then you have L3 cache. So, and then above the cache, if the cache runs out, you have RAM memory. Now, each cache line, because this memory is, the cache is divided into so-called cache lines, each cache line is actually 64 bytes or 16 bytes or 32 bytes, depending on the memory, the architecture actually. Therefore, when we have this stack, right, the stack is obviously the parts of the stacks are also loaded into the cache. So if you have the cache and the cache lines are here, given that this address is 4 and the cache lines are always aligned, That means that this variable on the stack will actually be put in one cache line. It's guaranteed that this variable is going to be in one cache line because the addresses of cache lines are divisible by, let's say, 16. Let's assume that our architecture is each cache line is 16 bytes long, and its address is also going to be divided by 16. So each time this variable, because just being aligned to an address ending with one of these variables, we are sure that it's going to be either at the end or in the middle, for example, at the end of a cache line, right, or in the middle of the cache line, but it's going to be in one cache line. Therefore, when the CPU fetches this value, the CPU will actually be able to, fetch it and basically, in one go, right? Which doesn't mean one cycle. It usually might be 1 cycle, 2 cycles, or 3 cycles, or something like that, but a rather small amount. Now, imagine if we would actually move this variable to a different spot. Let's assume we will move this variable to a spot which is not dividable by any of these numbers. For example, let's say we move this variable to an address. The first byte is at D, and then it's a 4-byte variable, right? So D would be the end of the address, and then the next byte would be on E, and next byte on F, and next byte would be on 0, obviously. Now, there's a huge probability that this kind of variable, which addresses of each byte aren't really aligned to the boundary of 4 bytes, are going to end up somewhere in, like, between two cache lines. And what this means is that when you access the variable from a CPU point of view, you actually have to access first the first cache line and then the second cache line. And you actually, in case these cache lines are not present inside in the CPU, then you have to you have to fetch it. So if they are not present in L1, then you have to fetch it from L2 or L3, and this might happen to both sides of the cache line. Therefore, just by changing the address of a variable, you're already making it 2 times slower, right? The access to this variable you are making 2 times slower. So instead of 3 cycles, as I said, for example, it differs from architecture to architecture. It might be 6 cycles. So let's do just that, and let's see how the time changes. We could actually do a chart, I guess, but let me comment this out for a sec. And let's just benchmark how long does it take to access a variable, okay? So going to copy paste the benchmark part. And I'm also going to do I'm going to set some value, and then I'm going to fetch, just read the value. I'm not going to write it. Yeah, but something else. It doesn't really matter what happens here. I'm thinking how to do it. Let's maybe do something like this. So, yeah. I'm going to make it an unsigned int. Yeah, D word. Just because it's defined what happens on overflow. Okay, so this is like simple math. And I want it to be done how many times? Quite a lot of times, actually. So 1,000 times 1,000 times 100 million times. And we'll time how long will it take now, and then we'll time how long will it take depending on the... We'll start changing the addresses. And yeah, and we'll see. So I still need to copy paste this, sorry, copy this. Let's see how it goes now. What? It doesn't like me because I did not copy this. This was not declared, therefore I do not need to do this, and this is unused, so I can comment it out as well. Perfect. Now, Yeah, so it takes this many cycles to actually... It's around, well, not cycles, I don't remember what was the unit. But yeah, in the end it takes this many units, or nanoseconds, or whatever that is, to, or microseconds, to basically sum up 100 million times the variable. It goes quite fast, right? So it's not cycles, definitely not cycles. Around 100k. So let's start shifting the address, and let's say if we can slow down access to it, and therefore in case of race condition we would extend the window of opportunity, the time window, if we are slowing down access to it, because for example on the check it will hang longer and giving us more time to change the variable. Somebody is asking why did I write this and not 1e8, because 1e8 is actually a double, and yeah, and I prefer to have an integer value here, just not to do the implicit cast. Cool. What do I do now? Then I need to change. How can you change the address of a variable like that? Well, you do something like that. Let's still keep it on the stack, because why not? Let's create a byte variable. Sorry, byte array actually, of size, I don't know, 128, because why not? I'm going to initialize it. This actually zeroes it. And now I'm going to do this, dword pointer, and this is the align, because it will be aligned to at least to the boundary of 4. So this will be an aligned address, but this address will be misaligned. It will be already misaligned, which means there will be probably already 2 fetches needed to be made, but it doesn't necessarily mean that we hit the boundary of a cache line. So let's see what happens now. This is probably not the best benchmark, but I'm going to run it a couple of times. Okay, and now I'm going to start increase it actually, and let's do it like this, in an automated fashion, somewhat automated fashion. Okay. I don't know. I don't think my cache line will be larger than 128. It has some side effects, but I'm going to ignore it for now. As soon as printf is actually like, this function does a lot of stuff, and really a lot of stuff, and it might mess up the cache timings quite a lot, but yeah, I'm going to, you know, probably the results will have to be kept in an array. Yeah, let's do it. So delta is going to have 128. No, yeah. Delta is equal to, okay. And I'm going to move printf out of the loop. This is a way too complicated function to be run in this case. There are no complicated functions whatsoever here. Query performance counter is rather easy. It's just rtdsc instruction with some math after that. But printf is touching all parts of memory, like due to buffering, due to other stuff. Maybe sometimes there's a kernel call just to do a flash into the output buffer. So this would mess up totally the cache layout between different experiments, like each run of this loop, so it would screw up the timings, and I don't want it, so I'm going to keep the printf out of the loop. And I'm just going to write out the results after we are already out of the loop. This will not screw up the timings. Benchmarking is hard. Yeah. This can be like this. Okay. Yeah, this should be fine. And it crashed. Why did it crash? What did I mess up? This is not fine. This is what's crashing it, because I didn't initialize it anyway before that. Yeah, and it's doing the experiment, and now we have the results. Now let's see if there is actually some difference on boundaries. I would expect the boundary to be around 13-ish. Doesn't seem to happen. There's the, yeah, this is like my expectations. This is a little higher than all the other ones. I might have forgotten RIJ, did I? Yes, thank you. Because the difference is too small. No, like, yeah, 10% difference. Let's do it again. So kudos goes to Jima. Now let's see. This should give some results. Hopefully, does it? No, it doesn't. It's not visible here. Why is it not visible here? Oh, here it's visible. Yeah, here it is visible. It means that my cache line on my CPU, on the architecture I have, is 32 byte. Because as you can see, as soon as it reaches the boundary, meaning that the first byte is actually on 29, the second byte will be on 30, 31, and 32. 32, we are indexed from 0, so 32 is already the second cache line, right? So, yeah, as long as it changes the cache, as you can see, the values here are greatly increased. And instead of 100,000, suddenly because we are attaching two different cache lines, the access to these variables is 4 times as slow as when it's compared to all the other accesses where the variable is actually will be on the same cache line. We're probably going to find the same thing around 64, so let's just go there. And nothing here, which might actually say that I have a larger... Oh, no, sorry, 32 plus 64 was 96. It should be here. Yeah, it is here, as expected. So again, the variable was placed between two different cache lines, therefore the slowness. Now, this is the first thing we can do, and we actually just increased the window of opportunity by a magnitude of 4, right? When exploiting a local race condition. What we can actually play a little better, because, well, I already told you about cache lines, right? But cache lines isn't the only thing that divides a memory. Another thing is called, well, you know, pages, virtual pages of memory. Each virtual page, as you know, is usually 4 kilobytes. And each 4 kilobytes are actually put, well, somewhere in a physical space, and another 4 kilobytes might be in a totally different area of physical space. And by physical space, I usually mean RAM. Sometimes I might mean something else, like the memory of a graphical card, for example, right? So we currently still are putting the variable on one RAM page, but what would happen if the variable would actually be put between 2 pages? Well, the system has to access 2 different pages. Now, what does that mean? Because that's actually quite interesting. This might, depending on the situation, this might make it from a little slow to super slow. And the best case scenario is that all of these pages, both this page and this page, are actually in level 2 or level 3 cache already, so there is no RAM fetch necessary, right? Now, so this is the fastest case possible. Or even they might be even both these lines, because this is still, like, might be split into lines. These lines are put in cache L1, which is even faster. A slower thing which might happen is actually when the it's nowhere inside in the cache. It's not in L3, L2, or L1. Then what you need to do is you need to fetch it from RAM. But this is virtual memory, and RAM is not addressed the same way. RAM is addressed, there's a translation table called the page table. So the page table is actually cached inside the CPU. There's something called TLB, is like look-aside buffer, table look-aside buffer. I don't remember the exact name, but yeah, it's called TLB. And when the CPU needs to fetch something from the RAM, it takes the address and looks it up in TLB. If it's in the TLB inside the CPU again, then it fetches it from the RAM. And this is the second thing. It's slower because you need to do well, TLB lookup is somewhat fast. Lookup inside the RAM, it's not. when I told you that you can think that fetching from the cache 1, a variable from cache 1, is actually around 3 cycles, then around, I think, 7 cycles with L2, and around 20 cycles with L3. When you start fetching from RAM, you are talking about 100 cycles upwards, like 100 to 200 cycles, for example, right? And again, if we go here, since we need to fetch this page of memory and we need to fetch this page of memory, that's actually two round trips to TLB, and also 2 times fetching from RAM, so that gives us already about 400 cycles. But things might get even worse, and things might get worse if the address which you want to translate from virtual address into physical address inside the RAM is not in TLB, because then what you need to do is you need to walk through the page table. The page table is a hierarchical structure basically, which like starts with a directory of tables, and then there's another level of indirection, and depending on which mode of the CPU you're running, if it's 32-bit, if it's 32-bit with a physical access extension, or if it's 64-bit, there might be even 4 layers of indirection here. Which means, and each entry is actually in RAM. Might be in RAM, might be in cache, but let's assume it's in RAM, because we are talking about the worst case scenario, right? So if you want to translate an address, you need to fetch first part from the directory, then fetch another from RAM, so that's already 200 cycles, then 400 cycles to like solve the second layer of indirection, and third layer of indirection gives you 600 cycles in worst case scenario, and then you need to fetch the variable that's 800 cycles up to 1000, let's assume, and then you need to do it twice because you just placed the variable between 2 pages. And each page can be on a different, well, for each page you can, well, most of these steps are actually the same, but the last layer of indirection will differ, so you get up to 1.5 thousand cycles just to fetch a RAM a memory variable, and we can actually check it. In my case, it will be in TLB. I will show you later how to, well, later in a second I will talk, because we are running out of time on the stream. But I'll mention how to invalidate TLB. Yeah, so, but to do it, it's actually going to be rather easy. I'm going to increase this number to 2 pages. 2 pages will be, let's say 5,000. Inside 5,000, there's a guarantee that there will be a page switch. But I'm not going to keep it here due to reasons. I'm going to keep it here and the same. Though it should be fine, I think, but whatever. The reasons being stack extension mechanism, which I did chat about a little on the last stream. So yeah, and now I probably should have a variable here, like a constant. And count is 5,000. I'm going to just use this here. And do I need to change this? Oh yeah, I'm going to change by an order of quite a lot actually, by an order of 100, because it would take too long to play with this experiment. And now I'm going to compile it, and I'm going to write it into a file just so we can browse it more easily. So output. Yeah, and that's okay, it's already finished. So this is the output, and what I will be looking for is, well, a rather large. This is a 4-time increase, so this is just the cache line boundaries, not the page line boundary, which page boundary, which I'm looking for. Nothing interesting. Another boundary in the cache. Nothing interesting either. I probably should like just sort it. Yeah, I probably should just sort it, or like run it through a Python script that will tell me where's the highest value. The value should be at least 5 digits though. So let me maybe do a regex, regular expression search. 9, but I want 5 digits. Yeah, here. This is the page boundary, assuming that in TLB, so the page table buffer inside the CPU actually has the pages. As you can see, the increase is from like around 1,000 cycles, or not cycles, like nanoseconds, whatever is the unit, to 25,000. So that's 25-fold increase already. And that's still assuming that we didn't reset the TLB, which we could do. So just placing the variable in the right spot in memory gives you this huge advantage in extending the time window just between, you know, two instructions in assembly, or three instructions in assembly. You can make them execute this long. Furthermore, when you're switching the variables, you can only switch the, because, you know, you have the variables in, like, let's maybe go back to the drawing program actually. Yeah, if you have the pages, right? So this is page 1 and this is page 2, then the kernel in this case has to access, well, both parts of the variable to read it, right? So it's really slow for him to access it. But as a racing thread, you can only change this part of variable. For example, if this is enough for you, then yeah, just feel free to change this. You never are touching the second page, therefore it will be really fast for you in comparison to the kernel, for which is going to be really slow. And you're also on the same cache line and so on, so access for your racing thread is actually like in the order of 1,000 of this, speaking in these numbers, right? But the kernel will still have access as slow as 25k units, speaking again in the terms of our experiment. So yeah, now how to reset TLB? There's actually invalidate TLB instruction. Now here's the catch. The invalidate TLB, which is this instruction, this is a kernel mode instruction. You cannot run it on your racing thread. What you can do is you can run kernel APIs or syscalls, which will actually run this for you. And there is at least one like that. I don't remember the name off the top of my head, but if we go to, so if we go here and open this, if we open this, I'm sure there's a section we have on TLB flashing. Oh yeah, empty working set. That's the API you can use, and it will flash TLB for you. That's cool. Okay, I'm going to go through the questions now, and after I go through the questions, I'm going to talk about like 5 or 10 more minutes about basically how to detect race conditions automatically, which we did in this paper, and then we'll just finish the stream. So if you have any ideas for the topic, well, I already told you what will be the topics for the next 2 streams, but still, if you have any ideas for new streams, then let me know in the comments under this video once it's on YouTube. Cool, so the questions, quite a lot of them actually. What's the best start for, what's the best way, I guess, for start with hacking? So for a person who gets basics of programming, what's the best way to start hacking? I guess the answer is war games and CTFs. So just try to solve some tasks there, and you'll basically need to learn the stuff as you go. And the tasks will tell you what you need to learn, right? If you're going after tasks from web security, you'll need to learn some web security and so on. Also, totally read write-ups on how to solve them for the first 20, for example, and then just try it yourself. So that would be my that's how I learned it. Okay. What about CTF 365? Is that a good site to learn hacking? I don't know. I never used it. It's basically a company who sells training courses in security, and they kind of attached to CTF brand or like genre or whatever you call it. I'm not too happy with them doing that, but yeah, well, they can use whatever name they like, obviously. Is there a way other than a proxy to load JavaScript file from local disk with every site open in the browser? I'm not I'm not sure what the question means actually, but like, I don't know, isn't that what, for example, browser extensions are for? Why did it crash? It crashed, so the application crashed because I forgot to initialize the pointer and I was dereferencing it. That's why it crashed. So the pointer was basically a null and it was dereferencing a null value. From a null address, which never exists, so it crashed. Here's a random question. Recently, I've been noticing some CTF challenges being revolved around Python bytecode. Does anyone, including you, have any resources to recommend? I'm sorry for what I'm going to say. I did publish a chapter in a book in Polish about just that, but it's in Polish. So I'm totally sorry about that. I hope it gets translated to English, but the publisher at this point is not interested in that. But yeah, maybe at the end of the year. Apart from that, I don't know, actually, what can I recommend? I mean, Python bytecode is trivial in the end. You can find, it's documented in the official documentation as well. The only thing I can recommend is just like play with it. It's seriously trivial. But I don't have any good resources, sorry. Okay, what about tricking branch predictor? Is it still possible? It's a good question actually about the branch predictor. I never played with it, so I cannot answer that question. I guess what new CPUs do is that instead of attempting to do a branch prediction, they also try to execute both branches at the same time, and then when it's clear which, and that's like execute it for the future without even the CPU reaching to that point, the real execution reaching that point. And then when it's clear which branch will be taken, they just discard part of the results and apply the other ones, commit the other ones. So I guess in that scenario, then it's not really possible if, in case of older branch predictions mechanisms, that's quite interesting. I cannot answer it, but that's a really interesting question, something I would have to look into. Windows Internals book is for Windows 7 as of now. What should I get to get information about kernel of Windows 10? Well, kernel of Windows 10 is still there's still quite a lot of code from Windows 7 there, and I don't know if actually, isn't the newest version about Windows 8 of Windows Internals? I actually don't remember, honestly. Apart from that, and from random websites, I don't think there's a good resource. We'll have to wait until the book is actually up to date. Will I participate in OCTF this weekend? Probably yes. I'm probably going to play OCTF or Zero CTF, whatever you're supposed to call it. So that was the end of the question. So I'm going to shortly talk about how do you detect race conditions in an automated fashion. Because, well, one idea is basically to look through the code, right? And see why. Well, this is one dereferencing the user memory, and this is like another dereferencing of the same address. That's a race condition. That's one way to do it. The way we actually devised with Euro, with Mateusz, because that was this research, that was something that we both did, right? As you can see here. It was different. What we did is we ran an operating system, Windows in this case, in box. Box being BOCSH or CCH. Yeah, box. Anyway, that's how you pronounce it. It's an x86 emulator. It's not a virtual machine. It's an emulated CPU, emulated hardware, which means that you are basically able to, by modifying it or writing actually a plugin as we did to it, you are able to instrument everything, whatever you like. What we instrumented basically memory accesses. So if you had a memory access to RAM or whatnot, right? And like forget everything about, I talked about TLBs, about caching, because in that case it didn't matter. It was instrumented at the moment when Box detected that it's going to be a virtual memory access. So for example, I don't know, like move and something. But it was only about read, so yeah. And we caught each instruction that was executed, and then we checked if the instruction is executed from kernel land So yeah, first thing it was like ring 0. Second thing it was, that was the most interesting thing. Second thing is that the target of the fetched memory region is actually placed in ring 3 memory. So it's going to do a kernel fetch of user memory. For example, exactly in the scenarios I described, this is what's happening, right? So you have an instruction on ring 0 which fetches memory from user memory, which I'm denoted in ring 3 memory, which isn't really a good definition, but you get the idea, I guess. And we noted all these things, and with each instruction we also noted like which syscall is it. Like syscall, Windows has a lot of syscalls. We also noted which thread is it. We also noted like the call stack, and did we note anything else? Like the size of access and some other things. And we got, a huge list of accesses on when the system was running. We got a huge list of accesses from kernel mode to user memory. And by huge, I mean the logs when we had the system running for 24 hours, running some fuzzers and whatnot of syscalls. It was 300 gigabytes around, right? And that was the largest, but we get more logs, obviously, from other experiments. And then what we are looking for is 2 accesses to the same address, not on the same instruction, right? But to the same address in ring 3, done within the same syscall execution in the same thread. Because if that happened, that means we have a talk to, or like a different kind of race condition where 2 accesses are happening to the same address in user memory, and this is probably a vulnerability. And by using this and filtering the 300 gigabyte log, we actually got, I don't know, like 20 to 30 bugs in Windows kernel and some default Windows drivers. You can read about some of them like in the paper. Everything is actually described here, like everything. This paper has like 70 pages. And then there were like also some follow-up posts by Mateusz and also a presentation, Black Hat, and presentation on SciScan. So there's quite a lot of documentation on this. So this is the easiest way to do it. And then another gentleman called Felix Wilhelm did the same, but what he did, he was looking for bugs in virtualizers as in hypervisors using a similar method. He called it Zenpone. So like Zenpone. You can look it up, I guess. He also talked about it on Black Hat last year. And he also found some race condition in virtualizers just using the same approach, but with his own tool, his own implementation. He did a really fine job there. So yeah, this is one automated way to find race conditions, I guess. You can also stumble on some false positives, for example, when... See the paper, there are quite a lot of false positives, surprising amount. For example, you fetch a D word, but then are using only 1 bit from it, and then you fetch it again, but you're using a different bit. That's not really a race condition because you're using different bits. And some other stuff. So yeah, I guess I'm going to give you the link to this if you're interested in reading it. Apart from it, look up the name, the boxbone name, just Google for it. The tool is by the way public. It's called KFetch Toolkit. Yeah, and it's here. You can play what you like. It's you have to compile it with box, though. I'm not saying it's easy, but you can do it. Okay, I see there's another question. So I guess. So there's a question about how branch prediction tricking would work. I guess the idea here is that it might be slower in case when the branch prediction fails. I guess that was the idea behind it. I like how Dohan says, I like how the PDF is called Boxbone, but I still couldn't spell it. I didn't look at the PDF name when I guess it was visible somewhere at the end, but I didn't take a look at it. But that's a good remark. Okay, so I guess that's it. Now, I guess there are no more questions. So if you If you have any questions, just leave them in the comments under this YouTube video, and next week is going to be Binary Ninja and writing plugins for it. If you have, and then a week after that, that will be format string attacks. Maybe the basics, maybe more advanced stuff. Let me know if you are interested in like the basics of format strings, or if you're interested into more advanced stuff of format strings. For example, when you don't control whatever's on the stack, and instead you have to deal with like the scenario that you have to use the things which are on the stack instead of controlling them, which is a more fun way to execute to exploit format strings. There's a question: you find the race conditions with symbols. I'm not sure what you mean by that. In case of our experiment, we did use like debugging symbols just to pinpoint where the race condition happened during the analysis process. But I'm not sure if that's your question. Okay, so in any case, that's it. So I'm leaving you with some music. Thank you again to KrzaQ for being the moderator today, and see you next week. Let me know what you think about this episode. Bye bye, and have a great evening or day wherever you are.